So hello Year 12, and firstly apologies for the slow return of these questions from a couple of weeks ago. I'm going to go through feedback on the questions on topic 3 and topic 4b, topic 3 Redox and 4b group 7. And I'm going to start by going through the multiple choice questions, focusing on the ones that you found difficult, and then I'm going to move on to the longer answer questions at the end. So, chemical reactions may involve oxidation, reduction, no change in oxidation numbers, or disproportionation, which describes what happens to chlorine. So here, chlorine in an element is 0. In HCl, it must be 1 minus because hydrogen's 1 plus except in a metal hydride. Here, oxygen's -2, hydrogen's +1, so therefore chlorine must be +1. So chlorine has gone from 0 to 1 minus and 0 to 1 plus. That is disproportionation D. 90% of you getting that right. Which of the following is not a disproportionation reaction? Okay, so here we've got chlorine going from 0 to 1 minus and 1 plus. Here we've got copper going from 1 plus to 2 plus and 0. Here we've got iodine going from 1 plus to 1 minus, and in this case that must be 5 plus. And so we're already suspicious that this must be the one that isn't a disproportionation reaction. Copper 0 to 2 plus. Hydrogen 1 plus staying as 1 plus. Oxygen -2 staying as -2, -2 and -2. So it must be the nitrogen. The nitrogen is going from 5 plus in this compound. It's staying as 5 plus in this one, but it's going down to 4 plus in here. But the nitrogen is being reduced. The copper is being oxidized. No one species is being simultaneously oxidized and reduced. So D, not disproportionation. Again, 90% of you getting that right. Which of these reactions is not disproportionation? Here we've got oxygen -1 going to 0 and -2, so that is disproportionation. Here we've got 6 minus, so the sulfur is 2 plus here, going to 4 plus and 0, so that is disproportionation. Chlorine 0 going to -1, bromide -1 going up to 0, so we're assuming that that's not disproportionation. Let's just check. Copper 1 plus going to 0 and 2 plus, yeah, it's C. So C is not disproportionation. Chlorine is being reduced, bromine is being oxidized, and 88% of you got that one right. The first one that was quite poorly done. Iodine can react with sodium hydroxide solution to form sodium iodate according to the reaction below. Which of the statements about the reaction is false? The oxidation of some iodine atoms goes up. Well, 0 to +5. Yeah, that's true. So that is true. Sodium ions are spectator ions. Yeah, they are. Na plus AQ. Na plus AQ, Na plus AQ. They're not doing anything. They are the spectator ions. Iodine goes down, yeah, 0 to -1, so that is also true. So the one that must be false is that at high temperatures, NaI also forms. What you should know is that the hotter the temperature, the more oxidized. So what you are more likely to form rather than NaIO is NaIO4 aqueous. Hotter the temperature, the more it swings towards the high oxidation states. And only 80% of you getting that right. And I presume that's after a few goes. I'm surprised this was badly done. Only 70% of you got this right. And I'm surprised this was so badly done, given that you have seen these questions before. In which of the following reactions is sulfuric acid acting as an oxidizing agent? That means it is reduced. Okay, so here, H2SO3, the sulfur must be in the 4 plus state. HSO3 minus, now it must be still actually in the 4 plus state, so there's no change there. Here, SO3 minus is 4 plus, SO2 is 4 plus, so again, no change there. Here, H2SO3, 4 plus, H2SO4 is going up to this more common 6 plus state, so there it is being oxidized, so it isn't that one, so it must be D by a process of elimination. Let's check. 4 plus, and the sulfur there going down to 0. Yes, it is being reduced, it is acting as an oxidizing agent, so D. And as I said, only about 70% of you getting that right. The thermite reaction shown below is a useful industrial process. The iron, well, it's going from 3 plus to 0, so it is being reduced. D, not well done, but I suspect that's because you were overcomplicating it. Which of these reactions is not redox? Well, I think we can say that this one is definitely redox. We've seen that before. So that is redox. Up here, magnesium nitrate. So the nitrogen in the NO3 is 5 plus. And in NO2 that's 4 plus. So that is definitely being reduced. The oxygen at -2 is going up to 0, so that is being oxidized, so that is redox. Sorry, that's A. C, iron is being oxidized, copper is being reduced, so that is redox. So it must be B. And we're not surprised by this because look, this is an acid and a base. And you should know a quick way to do this. Acid-base reactions are not redox. Remember in your group 7 stuff, there's always an acid-base reaction first between concentrated sulfuric acid and a halide salt, and then there's redox. So B, not redox there. But about 85% of you getting that right. Which of these following statements is, in which of the following reactions is sulfuric acid acting as an oxidizing agent? Again, we're looking for it being reduced. So here, 4 plus to 4 plus. Here, 4 plus to 6 plus, so that's being oxidized. Ah, look, we can see sulfur there. This looks familiar. 4 plus going to 0, it is being reduced. So it is C. About 85% of you getting that one right. Which of the following statements is true? Again, only 70% of you getting this right. And I suspect that this is because you haven't done revision. Which of the following statements is true? Calcium hydroxide is more soluble in water than magnesium hydroxide. Yeah, that is true. Calcium hydroxide is lime water. Sparingly soluble. Magnesium hydroxide is not at all soluble. And you should know your trending reactivity of group 2. Chlorine is more electronegative than fluorine. That is false. You should know that electronegativity increases that way and that way. More electronegative. Iodine is a stronger oxidizing agent than bromine. So, if something is an oxidizing agent, it is reduced. it gains electrons. So the question is, can iodine gain electrons more easily than bromine? No, it can't. You know that from GCSE. That is false. The first ionization energy of barium is greater than that of strontium. Absolutely not. You know that as you go down metals, they become easier to ionize. So again, that is false. What are the products other than water when chlorine is passed through cold, dilute aqueous sodium hydroxide solution? Well, it definitely forms the sodium chlorate 1 if it's cold, and the other thing it forms is sodium chloride. That's just knowledge there, and 90% of you did know that. It was shocking that only 3/4 of you knew this, though. There was no excuse for this to be so poorly answered. Cyclohexane used to test for iodine, left to stand. You should know that the upper layer would go purple. So iodine goes purple in an organic solvent. And underneath, you've got iodine water. Well, that would be a yellowy brown colour, but the only one it can be is C. And like I say, no excuse that only 75% of you got that right. Which of the following statements about the elements in group 7 is incorrect? They all exist as diatomic molecules. That's true, sorry. Electronegativity decreases as the group is descended. We saw that that is true. They all form acidic hydrides. So FH or HF, hydrofluoric acid, HCl, HBr, HI, that is true. So it must be false that they all show variable oxidation states in their compounds. You might be thinking, hang on, is that false? Well, think about fluorine. Fluorine is always 1-, always. That's one of your rules, so that's the reason why that is A, because of fluorine. You might not have thought of fluorine, but it's there. Which of the following properties of the halogens increases with increasing atomic number? So as you're going down the halogens, which of these increases? Boiling temperature, yeah, that does increase. And that's why we go from fluorine is a gas, chlorine is a gas, bromine is a liquid, and iodine is a solid at room temperature. Bond enthalpy, no, the bonds get weaker as you go down. Electronegativity, no, they get less electronegative. First ionization energy, no, it gets easier to remove. So it's A, about 90% of you getting that right. Which observations about silver chloride and silver bromide are correct? Right, well, when you add dilute ammonia, only the silver chloride dissolves. Concentrated ammonia, remember, will dissolve both of those, but not the iodide. So it's definitely A or C. So then you've got to remember this quirky thing about what does sunlight do? Well, both of them turn grey. So 31A, about 90% of you getting that right. I don't think that silver iodide decomposes. So silver iodide does not decompose in sunlight, but chloride, bromide and fluoride do. Starch is often used as an indicator in titrations between sodium thiosulfate and iodine solutions. What colour change would you see at the end point as sodium thiosulfate is added to iodine solution? Well, you should know that iodine solution starts off brown, and as it's diluted down, it goes orange, then it goes yellow, and finally, as it disappears, as it's used up, it would go colourless. So without an indicator, this would be the colourless. The colour. but starch is used as an indicator for iodine. It's the opposite of biology. In biology, we use iodine to show starch. In chemistry, we use starch to show the presence of iodine. And if there's any iodine, then it goes black or blue-black. So the colour change you would see is blue-black to colourless there, 33C. Only 3/4 of you getting that right, but I understand why. The best way to confirm the presence of iodine, not iodide. Okay, these would indicate the presence of iodide. So it must be adding hexane. Hexane with iodine forms a purple layer. Really, you should have all known that. So 34A, and 90% of you did. Okay, so now I'm going to look at the longer answer questions and the mark scheme. So if you've done these, stay tuned, otherwise you can tune it out. Right, Ionic equation for the reduction of chlorine molecules to chloride ions. So chlorine molecules, Cl2, to chloride ions. There must be 2 of those, and the charges clearly don't balance. You clearly need 2 electrons here to complete that. Write an ionic half equation for the oxidation of chlorine molecules to chlorate ions in the presence of cold aqueous hydroxide ions. This is really hard, okay? It's just, if you've never encountered it, it's going to be extremely impossible, and for 1 mark I'd skip it. So chlorine molecules to chlorate 1 ions, that's ClO minus, in the presence of cold aqueous hydroxide ions, okay? State symbols are not required. So we've got to ask ourselves, well, what is going to happen to the extra hydrogens here? That's got to go somewhere. And of course that will form water, H2O. Just making it balance, 2 of those. Chlorine, 2 ClO minus. So the chlorines are balanced. We've got 2 oxygens, 3 oxygens here. We've got to somehow make all of that balance. If we have 2 H2O here, then we can have 4 hydroxides, 4 hydrogens, 4 hydrogens, 4 oxygens, 4 oxygens. And then we've got to look at the charges. We've got 4 minus there, 2 minus there. So that must release 2 electrons. It's really difficult. It doesn't follow your normal rules. Don't worry about it. Combine the 2 equations in A1 and 2 to give the ionic equation for the reaction of chlorine molecules. Luckily, the numbers of electrons are the same. So it would be 2Cl2 plus 4OH minus going to 2Cl minus plus 2ClO minus plus 2H2O, and we could halve that if we wanted. And that should look a bit more familiar to you. Why is it disproportionation? 0 going to 1 minus and 1 plus. Different ion containing chlorine is formed when the hydroxide ions are hot. What is the chlorine containing ion? That is ClO3 minus, and the oxidation number there is 5 plus. So here's the mark scheme. Allow multiples, all that is correct. Explanation for this bit here. Disproportionation is both oxidation and reduction of a particular species. Chlorine goes from 0 to -1 and +1. Just make sure you put enough detail in. And chlorate, and chlorine is 5 plus. Bromine can be extracted from seawater containing bromide ions using chlorine. What's the ionic equation? Loads of you really struggle with this in your mid-unit test. I think it was like your January mock. But it's really simple. So bromide ions and chlorine going to bromine and chloride. And clearly you just need your 2's there. What's one hazard associated with this reaction? Chlorine is toxic. and a safety precaution would be in a fume hood. Something like that. So let's have a look. Chlorine is toxic, chlorine is poisonous, not harmful. Carry out the experiment in a fume hood, or bromine is corrosive, so you need to wear gloves. Make sure you know some safety. Physical states of chlorine and iodine at room temperature and pressure. Predict the physical state. You've seen this before. Chlorine is a gas, iodine is a solid, acetylene is a solid, and you've got to mention the London forces. Whenever you are asked for something like justify your answer for a trend in group 7, think, do I need to mention London forces? Allow for London forces, instantaneous dipole-induced dipoles, van der Waals forces, dispersion forces, induced dipole forces, but ignore references to stability or just quoting what the trend is. Write the equation for the reaction of chlorine with cold dilute sodium hydroxide to form bleach. Okay, you may have struggled with this, but chlorine forms the chloride, so we've got sodium hydroxide, NaOH plus chlorine. Hopefully you will remember NaCl plus, and it's cold, NaClO. The hydrogens must go somewhere, so H2O. We've got 2 sodiums there, so we need 2 sodiums there. We've got 2 hydrogens, 2 oxygens, 2 oxygens. There we go. Hydrogen bromide gas reacts with ammonia. What would be observed? You would see white smoke. Okay, make sure you're not confusing steamy fumes with white smoke. So white smoke would be seen, and there you go. 2 NaOH, Cl2, NaCl, NaClO, H2O. What is meant by the term electronegativity, and hence explain the polarity, if any, of the bonds? Okay, so electronegativity is the ability of an atom to pull a bonding pair of electrons towards itself. So if you've got, for example, fluorine-chlorine bond, fluorine is going to be negatively charged, carbon is going to be positively charged. So, an explanation that makes reference to the following points. Electronegativity is the relative ability of an atom to attract the bonding electrons in a covalent bond. Fluorine is more electronegative than chlorine. ClF3. Aha. So chlorine, yeah, fluorine is more electronegative than chlorine. Fluorine's the most, I've read that as ClF3. Fluorine is more electronegative than chlorine. Fluorine is the most electronegative element. So fluorine is partially negatively charged. Chlorine is partially positively charged there. If you talked about fluoride or chloride, you would be penalised for that. If you know the absolute electronegativity is good on you, but it wasn't needed, could be shown on a diagram as I did. Number of ions in 9.53 grams of magnesium chloride, 9.53 divided by 95.3 gives you 0.1 moles. So times by 6.02 times 10 to the 23 is 6.02 times 10 to the 22 particles. And of course there are 3 ions, so times that by 3, 1.81 times 10 to the 23 ions. That's how you do that. You've seen this before. We've gone through this for the group 2 stuff. Potassium chloride would give a lilac flame because of the potassium. That's the correct diagram. White precipitate barium chloride used to test for sulfates. And 2 of the solutions with nitric acid, you're testing for halides. You would get a white precipitate with hydrochloric acid and potassium chloride, as they both contain chloride. If you react the hydrochloric acid with a carbonate, you would see fizzing bubbles, effervescence, and that is the Ionic equation there. 2H plus plus CO3 2 minus goes to CO2 and H2O. Okay, You've seen that recently. Now to the slightly longer questions. Potassium dichromate can be used to accurately determine the concentration of other chemicals such as sodium thiosulfate. It's got 2 chromium atoms sharing 1 oxygen. Each chromium atom uses 6 electrons in bonding and expands its outer shell to accommodate a total of 12 electrons. Complete the dot cross diagram. Only show the outer shell. Use X for chromium and dot for oxygen electrons. Okay. So it's got 2 minus, so we know there's 2 extra electrons. We know that chromium's using 6 electrons in bonding. So oxygen needs 2 more. So X for the chromium, dot for the oxygen. Okay, that oxygen's happy, got 8 electrons in its outer shell. What's going to go on here? Well, let's assume that chromium uses another 2 of its electrons. An oxygen there, double bond there, that's happy. This one down here though, okay, we've got 2 oxygens, so let's assume that chromium only uses 1 electron for each of those. Well, at first glance this doesn't appear happy, this oxygen, because it's only got 7 electrons. But we've got the extra electrons, so I'm going to do an asterisk there for the extra electron. Let's mirror that on the other side. Double bond to that. Double bond to that. 2 electrons left. We'll make 1 bond to each of those. Oxygen at first looks unhappy. Asterisk. Yeah, perfect. Everything's sorted. So here we go. Correct number of dots and crosses around both chromium atoms will get you 1 mark. Making sure that there are 12, of course. So 4, 8, 10, 12 electrons. That works well. Extra 2 electrons from the oxygen atoms have the correct number of bonds and lone pairs. Yeah, of course, making sure that's true. Extra 2 electrons are on the oxygens, okay? So don't forget those, 3 marks. 4 chemistry students were given a solution of sodium thiosulfate, concentration approximately 0.1 mole per dm cubed, and asked to determine its exact concentration. First student was given a task of making up potassium dichromate 6 solution. Mass of 14.71 grams of potassium chromate was weighed out, dissolved in deionized water, made up 250 centimeters cubed volumetric flask. Calculate the concentration. Well, you're basically going to use moles equals mass over mR, and then conc is moles over volume, like that. Don't forget to put the volume in decimeters cubed. The second student was asked to calculate the mass of potassium iodide that would be required to add add 0.00025 moles of potassium dichromate to ensure complete reaction. There's the reaction. So we've got 0.0025 moles of that. The iodide, okay, so we need 6 times that. So 6 times 0.00250 gives us the number of moles of potassium iodide we need. Doing that in my head is going to be 0.015 moles. And so we can work out the mass, therefore, by moles times mR. But then we want to add maybe like a 10% excess. So don't forget to add a little bit extra. So let's have a look. 0.15 moles. Moles is mass times mR. Okay. 2.49 grams. And as long as you have got an answer between 2.6 and 5, so that is sort of from a 10% to a 2-fold excess, you got the second mark. Third student did this. Student was asked to estimate the titration reading at the end point of a solution that contained 0.0026 moles of iodine, was in the conical flask. Concentration of sodium thiosulfate was about 0.16 mole per dm cubed. Calculate the volume of sodium thiosulfate solution that would have been added at the end point of the titration. So this is slightly unusual in that you're not given concentration and volume of iodine. Instead, you're just given the total number of moles of iodine. Okay, so we know the total number of moles of iodine is 0.00260. So therefore, that's going to need 0.00520 moles of thiosulfate. And then volume is moles over concentration, and that will give us the volume in decimeters cubed, so we can just convert that into centimeters cubed. So there you go, 0.0325 decimeters cubed, and volume must be at least 3 significant figures for all those marks. Fourth student was given this: 0.1 gram of potassium dichromate dissolved in total volume 25 in excess of potassium iodide and acid was added using the titration with the sodium thiosulfate solution of concentration approximately 0.1 mole per dm cubed. Titer was 25.15. The student suggested that the greatest uncertainty in the result arose from the mass that was measured and that the procedure was unreliable. Explain why these views were justified. No calculation is required. Okay, so looking at these values, we've got to work out the greatest uncertainty. Well, when we look at this 0.1 grams, the error in that is going to be about 10%. These values are far more precise here to several significant figures. You might be wondering why we don't worry about the fact that that is only to one significant figure. Well, I think that is what we're going to find. So we know the amount of potassium dichromate, we're going to titrate it against that. So we're going to work out what the exact concentration is. So that doesn't matter that that's inaccurate, we're going to find that out. But this does matter. I'm not quite sure what the mark scheme would want. Percentage error is large with such a small mass. Mass is to only one significant figure. There we go. No repeats possible. That's interesting. So you could have had 1 mark for saying that it was not possible to repeat it. Well, you were supposed to have 1 mark for saying that you couldn't repeat it if you did it this way. Ionic equation for the oxidation of chloride ions to chlorine. So chloride ions are oxidized to chlorine. So Cl minus going to Cl2. 2 of those must release 2 electrons. Fumes of hydrogen chloride gas can be identified by bringing the fumes into contact with another gas X. So this would be ammonia, and you would get white smoke. Not misty fumes, you would get white smoke. There you go. So white smoke, dense white fumes. Potassium bromide can be distinguished from potassium chloride by its reaction with silver nitrate solution, followed by the addition of aqueous ammonia solution. What would you see on the addition of silver nitrate solution to potassium bromide solution? So you would see, when you added potassium bromide and silver nitrate, you would see a cream precipitate. How could both dilute and concentrated ammonia be used to confirm that silver bromide is formed rather than silver chloride? So you would add NH3 dilute, and it should not dissolve. Unlike the chloride. Then you would add NH3 conc, and it will dissolve. There's quite a common misconception that the chloride won't dissolve in concentrated ammonia, but of course it will. It's just that the chloride will dissolve both. Bromide will only dissolve in the concentrated stuff. So cream precipitate for 1 mark. It will remain in dilute but dissolves in concentrated, 2nd mark. But you needed to say silver chloride dissolves in both, and I bet many of you would have missed that final mark. Okay, last question. Chlorine is used to prevent the growth of bacteria in a swimming pool. Reacts as shown below. Why is it disproportionation? 0 to -1 and +1. Chlorine, both oxidized and reduced. Okay. State and explain the effect on the position of equilibrium if concentrated hydrochloric acid is added to a sample of chlorinated swimming pool water. So, from Le Chatelier, if you are adding a product, hydrochloric acid, then the equilibrium will move to the left. So, if you add hydrochloric acid, the equilibrium will move to the left, forming more chlorine and water. So let's have a look at that. Chlorine is 0, goes up to +1 and -1 for 2 marks. Third mark is for saying the same element is both oxidized and reduced. Equilibrium moves to the left. To use up some of the added HCl, to react with added HCl, to decrease the concentration of products, okay? But unfortunately, you couldn't have, to counteract the change in the system, you couldn't just say because of Le Chatelier, I'm afraid. So I probably wouldn't have got that mark. In a similar reaction, chlorine reacts with sodium hydroxide to make household bleach. Complete the ionic half equations below for the reaction of chlorate with acidified potassium iodide by balancing them and adding electrons where required. Okay, chlorate, chlorine, we've got 2 hydrogens, so we need 2 protons here. On the left hand side, we've got an overall charge of +1. We've got -1 there, so we need to add 2 electrons here in order to get the left hand side -1 and the right hand side -1. Over here, we must have 2 iodides. That releases 2 electrons, and happily, they both have 2, so when we write the thing together, ClO- plus 2H plus 2I- goes to Cl- plus I2 plus H2O. Number of moles of iodine in the solution. Moles is concentration times volume. Remember to put the volume in decimeters cubed. And what is the number of moles of chlorate ions in the sample of diluted bleach? So we know about the iodine requiring an average titer so that's the iodine that is produced. So it's a 1-to-1 ratio. One of those produces one of those. In fact, and moles of ClO- is the same, okay? So they were allowing you to have an answer if you got the ratio wrong in that step. Hence calculate the concentration in moles per decimeter cubed of chlorate in the undiluted bleach. You've got the moles, you've got the volume, so concentration is moles over volume. Moles over volume there. 1.5 grams of potassium iodide contains this number of moles of iodide. Use your answers to B2 and B4 to show by calculation why this amount was unsuitable. Okay, so our answer to B4 is the number of moles of chlorate. Chlorate 1, 6.05 times 10 to the minus 4. So ClO minus 6.05 times 10 to the minus 4. And B2 tells us that the ratio is 1-to-1. So therefore you've got about a 15 times excess of iodide. Okay, so looking back at the question, we want, if you look back here, we need all of the chlorate to react. So we need all ClO minus to react to form iodine. and therefore this large excess is desirable. The iodide will ensure that all the chlorate forms iodine. That took me quite a while to work out what was going on there. Student carrying out this titration measured the mean average titer as 24.5 centimetres. What is the percentage difference in the student's titer compared with the accurate value of 24.2? So the percentage difference would be 24.50 minus 24.20, which equals 0.30. You divide that by the accurate value 24.20, and then you times that by 100%. And so you would get an answer of 1.24 or 1.2% there. Looking at the answer here, moles of iodide is more than, so they want you the minimum amount of iodine to react with OCl. The OCl is 2 times the answer to that, and the moles of iodine is far more than this amount, so the iodide is in excess, so that all the ClO- can react. Okay. Very finally, the difference between the student's mean titer and the accurate value was not due to the limitations in the accuracy of the measuring instruments. Suggest one possible reason for this difference. Okay, so why is he going to be slightly out by about 1% in this reaction? Possibly slow reaction. Maybe an impure chemical. I'm not sure what they want. We'll find out in a sec. Suggests one damaging effect to the upper atmosphere which could be caused by the presence of chlorine compounds that typically they destroy the ozone layer. Think CFCs. Okay. So judgment of colour change at the end point, adding starch too early in the titration, jet of the burette not filled. Errors must cause an increase in the title. Reject, some potassium iodide did not dissolve, leaving a funnel in the burette. Errors which affect both the student's titer and an accurate titer using the same solutions, e.g. impure solutions. I would not have got that mark. So what they're suggesting is that they've overestimated because the end point was not obvious. And there you go. Chlorine radical breaks down the ozone layer. Alright, I hope some of that was helpful. Particularly this last question I didn't find easy myself. So don't worry if you found it difficult too. Good luck with your preparation for the end of year exam next week. Do email me if you've got any problems. Goodbye.